dispatch. Okay. So now let's start the ELD issue or continue with the ELD issue. So what was the problem in the ELD? Let me reiterate that problem. So our problem was there basically to minimize the cost, right? We were targeting to minimize the cost. And we had to satisfy an equality constraint between generation and demand. If you recall, to begin with, we are ignoring any losses as well as we are ignoring the generation limits. So we only left with the generation, summation of all the generations equal to demand. And keeping this constraint in mind, we have to look out for a minimum cost solution. Okay, this was the target. So we can say this is my f of x and this is my g of x. Okay. Yeah.
So I would like to ask, why have we done like the graphical representation of the gradient? Is it really needed, or you just did it to show us how things are going?
The graphical analysis?
Yeah.
No, it's not needed. It is for your understanding.
Okay, sir.
It's not mandatory. Okay. It's not mandatory, but it is mandatory for understanding. But for solving the problem, it's not mandatory. If you know the techniques, these are available anywhere in any math books or any economics book, any optimization book, you can simply apply them. But for understanding the Lagrangian, okay, understanding the Lagrangian, I actually went through all the gradient fields and other things. Okay, is that okay?
Yeah, it's okay.
Okay, thank you very much. So this is our f of x, and this is our g of x. So can anyone tell me which one is the x variables there?
PGI.
Excellent. So PGI, that means the generation output from each of the generators. We can easily treat them as our xi, x1, x2, x3, pg1, pg2 up to pgm. Okay. So this is my f of x. Here it is function of PGI. Okay, and this is my g of x. You see here also I have presence of the x variables or the PG variables. And I should write it in terms of g of x is equal to 0. So how should I rearrange this? I should rearrange this either like PD. Remember the P loss is 0, okay? P loss is 0 as mentioned here. To begin with, P loss is 0. So we only have PD here on the right hand side, and the left hand side we have summation of PGI. So simply write PD minus summation of PGI is equal to 0. This is how we are going to formulate our g of x function. So then, as we said in the optimization slide, we are going to define the Lagrangian in this fashion, same fashion, and we are going to look out for satisfying these two conditions, okay, simultaneously. This is the necessary first order optimality condition. Why it is called first order? Because we are taking the first derivative of the expression. That's why it is first order optimality condition. Similarly, you might also experience second order optimality condition. Can anyone tell any example of second order optimality condition which we have already discussed in this course? Can you recall in one of our earlier lectures?
Dissociation condition.
Sorry?
Taking the second derivative.
Second derivative, yeah. Did we take second derivative anywhere?
Or maxima and minima?
Yes,
yeah, exactly. Yeah, exactly. In the Hessian matrix, okay? In the Hessian calculation, I mean, if I want to find out whether it is a maxima or minima explicitly, then we have to go for the second order optimality condition. But here we are only taking the first partial derivative of the gradients. So this is the first order optimality condition, okay? Okay. So now we form our Lagrangian expression. So we have, instead of using x, arbitrary variable x, I have included here PG and lambda. So the first part was if you remember, it was f of x. So this is my f of x, summation of costs for all the generators which are function of x variables or generation output variables, plus lambda into g of x. So you see this is represented as g of x equals to 0. So it is rewritten like PD, which was on the right hand side, was in slide number 12. You see it is written like PD minus this thing taken on this side, P losses is 0. So on the left hand side, you will be left with 0. So this is f of x plus lambda of g of x. This is my Lagrangian on slide number 15. Okay. It also mentioned that there are no losses considered. If there are losses, then this expression will be a little bit slightly modified, okay, which we will take later on. So the necessary conditions, again, you have to take the partial derivatives or the gradients, you have to calculate and you have to equate them to 0. So after you calculate this, in general, this is what you get back. Okay, you have the gradient of f of x plus lambda into gradient of del g of x. This is we have already shown for the earlier example today. And the second condition always gives you back the equality constraint. G of x is equal to 0. Okay, g of x is equal to 0. So now you have to calculate this gradient of f of x and gradient of g of x. So this gradient of f of x would give you what? The gradient of f of x would give you, if you look at the function c of ci pgi, simply it would give you dci over dpgi expression. Okay, why this is such? You see, I'm not using any partial derivative di. Okay, instead I'm using the d expression. I explained it in one of the earlier classes, because you see, if in this slide, if you see in this slide number 16, C1 is a pure function of PG1. Okay, it has nothing to do with PG2. Whatever generation is provided from generator number 2, it is in no way going to affect the cost for generation 1 and vice versa. Okay, so you can say C1 is purely a function of x1. Okay, considering this is my variable x1 and this is my variable x2. So these are my x variables, x1, and this is x2. So if I take the partial derivative, okay, here, in terms of, let's say, di C1 over di PG1, what will be left? The thing that would be left is simply some function of x1, okay? There is no x2. Clear?
Yes, sir.
Similarly, if I take the partial derivative, di C2 over di PG2, I'm only left with some function of PG2. So simply I can say, instead of taking a partial derivative of di C1 over di PG1, I can simply write it like dC1 over dPG1. Okay, that means an ordinary differentiation, not partial differentiation. For this case, for this example of economic dispatch, that is true. Okay, but may not be always true. For this one, it is true. So simply we can write it as dCi over dPgi, means I equals to 1 up to m. Yeah.
Sir, for in general condition, we have to take the partial derivative.
Yeah, the general condition I mentioned in the earlier example, because we had a multiplication of x1 and x2 there. You remember, x1 is square x2. So you had to take partial derivative because the cost function was, I mean, the variables x1 and x2 were in multiplicative form. Here they're in additive form. Okay, that's why they are not appearing in the other expression.
Yes, sir.
Okay, that was the general case. This is one specific case where you can take, instead of di, you can simply take d. Okay,
Yes.
ordinary differentiation, not partial differentiation. And this del g of x would simply give you back the lambdas. Okay, if you take the derivative here, partial derivative of this expression, that means if you are going to calculate this part, okay, LPG of lambda, this is your LPG of lambda. Where is the lambda appearing? Only here. So the first part will not appear, and you will simply get back your PD minus this. This is your second condition. And if you take the partial derivative, so this one is basically this one. You are getting back your g of x, your constraint function. Then you are going to take del g of x. Why you need del g of x? Because you have to put it here. Basically, this should be actually 1. Okay, there is.
You guys went out.
Yeah. So there is. Thank you for the comment. It should be 1. Okay, so it should be 1. Okay. So because you see, there is no lambda. Actually, I made a mistake. Sorry, I made a mistake here. So there is no lambda. So if you take the partial derivative only, you are going to get back the corresponding. If you take the derivative with respect to PGI, okay. So on, if you, let's say here you have PG1 plus PG2 up to PGM. If you take the partial derivative, simply you take, if you differentiate, take the derivative with respect to PG1, you will get only 1. Because of this minus, you will have a minus, okay, and so on. So that would be -1, not lambda. Okay. So then this is specific with some specific values given. So your demand now, we are going directly into problem solution. You have a demand given, you have 2 generators, so PG1 plus PG2, you have to satisfy the demand of 500 megawatt from your available 2 generating units. And for each of the generating units, you have the cost functions given in dollars per hour. So now you apply the Lagrange multiplier method. So simply you calculate whatever, the theorems I have mentioned here, you simply go through those. Okay. So what we form basically this one, okay? Del f of x plus lambda del gx, okay, equals to 0. So lambda del gx is actually -1, and there is a multiplication of lambda, okay, and the dimension would be m by 1. So because you have 2 generators, you will have 2 equations. I is equal to 1 up to 2, okay. So you are going to calculate this one, and then because of the minus here, if you plug the values here, del g of x here and del f of x here, so you will get some minus sign, okay, because of this -1. So this is what I am doing. Taking the partial derivative, as I said earlier, is simply taking the ordinary differentiation of this cost function with respect to PG1, and because of the minus, there is a minus lambda. That should be equated to 0. So dC1 over dPG1 is nothing but how much? 20 plus the 2 will come down here. So 0.02 minus lambda equals to 0. We take the derivative for the second one. You can easily calculate that. Equate them to 0. Equate it to 0. And the third condition is coming because of this. Okay. So the first 2 equations are coming because of this. The third equation is coming, simply the equality constraint is re-arriving here. So this is the third condition. How many unknowns? 3 unknowns. You have to calculate PG1, you have to calculate PG2, and you have to also calculate lambda. So 3 equations, 3 unknown. You can simply use the matrix formulation, which I have used here. Okay, simply use the matrix formulation. So you formulate your matrix. You take PG1, PG2, and lambda as your unknown variables. You just you fill up the matrix with the corresponding coefficients, and of course take the constant values to the other side. Okay, so the first expression you have only PG1, its coefficient is 0.02, no appearance of PG2, so it is 0. There is a 1 lambda with a minus sign, so it's -1, and so on. Okay, remember you have to take these 500 to the other side. So this is the matrix here, filled up by the constant values, and then simply you take the inverse of this, take it to the other side, and simply you get the result. Okay. Any question up to now? No question. Okay. So now let us go to a more generalized process of solving this economic dispatch problem. The process that we have shown here is easily applicable for equality constraint type problem. Okay, you will get simply linear equations, and you can simply form the matrices, and you can easily calculate the required unknown variables.
Excuse me,
Okay.
sir.
Yeah.
Sir, Can you please come back to the third condition to form the third equation? Because I didn't get it. You said P.
This equation,
Yes, sir.
okay. How is it coming?
Yes, sir.
This is nothing but this one, okay, this one. This is the equality constraint equation. So PD is how much? 500 given. PD is how much? 500. So this is PD given, okay?
Yes, sir.
So you have to formulate it like PD minus summation of
PG1
PGs, okay? So this is the summation of PGs. This is how it is coming, okay?
All right, sir. Thank you very much.
Okay. So now we look and try to solve this problem. Of course, we'll take another example. But now we will be solving using another method which is known as the lambda iteration method. Why we need it? We need it because this method is also applicable for inequality constraints. Okay. Later on, when we will incorporate inequality, by inequality I mean, let's say we incorporate the generation limits, maximum generation possible, minimum generation possible. In those cases, the solution method that we used here in this example, that is not applicable. Okay? But the one which we will start now, the lambda iteration method, because this is an iterative method, this is still, this will be still applicable for those inequality constraint problems. Okay, so it is always a good idea to have different techniques in your armory. Okay, so that you can apply it for more generalized problems. Okay. So let's go through now this process. In this case, because it is an iterative technique, what we will do, we will first assume different values of lambda here. Okay? And then we will go through very, what should I say? Very few steps. Okay? Within 1-2 steps of the algorithm. The algorithm doesn't contain very large amount of steps. Okay? Within 1 or 2 steps, we can simply solve our problem. But because it requires iteration, so that's why the name is lambda iteration. Okay, it is an iterative technique of solving the economic dispatch problem, and we are going to iterate for the values of lambda. Okay, so we are going to basically update the lambda value, and like any other iterative technique, we are going to look for some convergence. Okay, we are going to define some error function, and with the updating of lambda value, we are going to find out some diminishing value or converging value of the error. Okay, so let's see how we are going to do this in this slide. So this is in short the steps of the lambda iteration algorithm. As you can see, very few steps are required. Okay, it's not a very large or long algorithm. Computationally, it's not very involved. Okay, rather it's very simple technique. Let's go through it. So the first step is a little trivial one. You have to pick 2 values of lambda. Okay, 2 values by 2 values of lambda. One I'm denoting lambda L, another one is lambda H. By L I mean some lower value, H stands for some higher value. So in what respect they are lower and higher? In this respect. Okay, as I said, we are going to minimize some error function. Okay, what is the error here? What is my target? My target here is to reach or satisfy this demand. Okay, satisfy this demand with the help of my available generations. Okay, so I'm going to define my error function as this one. In this algorithm, I am going to define the error function for our problem. This is my error function. Okay, up to this point. So the difference between the generation, summation of the generation and demand. Okay, this is my error function. I am trying to minimize this error as much as possible. Okay, the best is that exactly they are matched. This is the best possible solution. Okay, now because I don't know what would be the exact value of lambda to start with, so I have to pick 2 lambdas. Okay, for this algorithm I have to pick 2 lambdas. One lambda would satisfy this condition, the first condition here. What is the condition? That if I put that lambda value here in the expression of PG, summation of PG, And if I subtract it, if I subtract PD from that expression, then I should get some negative value. That lambda would be my lambda L. Okay. And I pick another lambda which is higher than lambda L, such that this error function becomes positive. Okay. So basically I am taking one lambda value in such a way that my error is negative, another lambda value which is giving me positive error. So what is my target? My target in the next few steps would be to go through some iterative algorithm, and try to minimize the gap between lambda L and lambda H. Are you getting my points? My target is to converge these lambda L and lambda H to such a point where this error becomes exactly zero or very negligible. This is my target. That's why I am taking values at two ends of my actual solution. Okay? My actual solution is in between lambda L and lambda H. Okay? The actual value of lambda, desired value of lambda, which would satisfy this condition, PGI, summation of PGI is equal to PD. My desired lambda would be in between lambda L and lambda H. Okay. So now let's start the algorithm. So I now check this condition. Okay. If lambda H minus lambda L, this absolute value is greater than epsilon. Epsilon is my convergence criteria or tolerance value. For any iterative algorithm, you need to define some, you can say, stopping criteria or convergence criteria. I mean, when will you stop? Okay. When would you stop? This is the stopping criteria or convergence criteria or tolerance. How much error will you tolerate? Okay. So because this is a minimization problem, we are trying to minimize this gap. So it is better to keep epsilon as small as possible for our problem. Okay. So while this condition is satisfied, you do the following. Okay. You take another, you calculate another lambda as an averaged value of the two. Okay. Average value of lambda high and lambda low. You get a new lambda. Okay. Now you take this updated lambda and you plug it in your error function. This is your error function. Okay. Now you plug it in the error function. So instead of putting lambda L or lambda H, you put the newly calculated lambda here, lambda M. And now you check the condition. If this new lambda gives you positive error, okay, gives you positive error, then what you do? You reduce your higher value of lambda and you set it to lambda M. Or if this condition is satisfied, the lower condition means if after putting the lambda M, the updated lambda here, after putting it into your error function, if it is still negative, that means you have to increase your lambda L to the newly calculated value of lambda M. And that ends. This is how simple it is. Okay. Just you have to check these two conditions in each iteration. At the beginning of the iteration, you have to satisfy this while condition. Now, when the algorithm will stop, when this condition is satisfied, you will end your while loop. Okay. And in between, you calculate, you update your lambda.
Sir.
Yeah.
Sir, like if the first equation is satisfied, then lambda H will be lambda M.
Yeah.
So then what will be the lambda L?
Lambda L will stay as it was in the previous iteration.
Yes, sir.
And similarly here, very good question. And similarly here, if this condition is fulfilled, lambda H will remain as it was in the previous iteration. Okay. Immediate previous iteration. Clear?
Yes, sir.
Okay, thank you. So graphically, what it is actually trying to do, let's say you have 3 generating units, okay? 3 generating units having 3 df over dp1. What is f? F is the cost function. What would be then df over dp1? Which sort of curve is this? What is the physical meaning of this? If f is the cost for generation unit 1, P
It's
is
the
the
incremental cost curve.
excellent. This is the incremental cost curves. Okay. incremental cost curves. So basically what I'm trying to do, I'm trying to slide along. If let's say this is my current position, okay, these are the incremental cost curves, okay, incremental cost curves for my 3 generating units. What I'm trying to do, I'm going to try and slide along these lines simultaneously, okay, simultaneously. You see their shapes are different, okay, their cost functions are different. That's why their incremental cost curves are also different. So I'm going to slide along these curves. At the same time, whatever generation is coming out, I'm going to sum them up and I'm going to satisfy the required demand. Okay, so when I will stop my sliding, whenever this value P1 plus P2 plus P3 is exactly equal to P demand or PR according to this diagram. Okay, so I'm going to slide. If I go up, I have to go up here also, I have to go up here also. So you see, accordingly my P1, P2, P3, they are also varying. Do you get the point? So this is the graphical explanation of the lambda iteration algorithm. Now, let's take one example, very simple example. So instead of giving you the cost functions, straightforward, in this example, they are giving you the incremental cost function, okay? So you see the cost function was something like some constant plus some other constant multiplied by PG1 plus some other constant multiplied by PG1 square, okay? It was a quadratic function. The incremental cost is simply a first order equation. It's a function of PG1. Okay, so let's consider a 3 generator system giving with information given in terms of the incremental cost function. Now you see at each equation, beside each equation, we are equating them to lambda. Why are we doing this? Anyone can answer this? I mean, why? I mean, suddenly, why we are equating them to lambda and same lambda? Did we
Sir,
discuss
in the
this?
Lagrangian equation, the g
Yeah,
of x equal
yeah,
to
yeah.
-1.
Yeah, excellent. So in the Lagrange, if I just go back few slides, let me just, so this one, yeah. So you see, this one is what? This one is my incremental cost function for generation 1, generator 1. This is my incremental cost function for generator 2. And if I take this lambda to the other side, what do we get? We get the same thing. Incremental cost for generation number 1, incremental cost for generation number 2, all are equal to the single lambda. So already actually we have learned this condition, that we have to satisfy this condition, right? That's why we are directly using it for solving this problem. It is nothing new. So at the optimal point, your incremental cost for all these generations should be equal, okay? And equal to lambda variable, the Lagrangian variable. And the constraint is given in terms of P demand. So your 3 generating units should sum up and give you exactly the 1000 megawatt required. So you see that while we were talking about this algorithm, we expressed the lambdas, sorry, we expressed the PG in terms of lambda, right? So to take help from this algorithm, or to be able to use this algorithm, we have to somehow relate PGs and lambdas, right? Because PGs are a function of lambda. So keeping this in mind, we go through, we start here again, slide number 21. So what we do simply, we rearrange these expressions, okay? And we simply express PG in terms of lambda, PG2 in terms of lambda, PG3 in terms of lambda. This is what is done here, okay? There's nothing special. Just we are rewriting and representing our PGI, the desired variables, unknown variables in terms of lambda. And then what we do, it's simply iterate this lambda. We'll add PG1, PG2, PG3, and we'll check whether the demand is fulfilled or not. This is as simple as that, okay? This is where the lambda updating will be happening. Accordingly, your PG1, PG2, and PG3 will be updated. And at some point of iteration, your demand will be almost or exactly matched, depending on your tolerance value, okay? This is how the algorithm will work. So now let's pick 2 values for this example. these 20 lambda L is taken as 20, okay, which gives us lambda L20, yeah. So lambda L20 gives us this 600 minus 670, okay, minus 670. What is summation of PGI, function of lambda? Remember, PGIs are now this. So what we have done there, we have simply put lambda equals to 20 there, okay, 20, 20, 20. And then we have subtracted 1000 from that summation, and we get some minus value. So we pick it as our lambda L. Remember, lambda L condition has to be satisfied by this expression. Okay, lambda L should be such that this error function becomes negative. Okay, so 20 satisfies this. And take it. We try lambda H, some higher value 30. It also satisfies this condition. Okay, lambda H, with this lambda H 30 equals to 30, our condition satisfies, which is greater than 0 because it is positive. So now we have got lambda L and lambda H. So we start our iteration. Okay, so for this problem, I have actually used a very small epsilon, okay, to have a good result, good, solution, good convergence. So picking this epsilon, we start the iteration. So we
Sir.
check this, yeah.
20 আর 30 কি randomly ধরবো?
You have to choose in such a way that this condition is fulfilled. You could take 22 and check this. You could take 28 and check this, okay?
Yes, sir.
So you can take any value which satisfies these two conditions, okay? Simultaneously. Lambda L has to be satisfied here, less than, and lambda H has to be satisfied here, okay? Then you check the first condition, lambda H minus lambda L. Remember, lambda H is 30, lambda L is 20. So of course, this is greater than, this is small value. So we calculate lambda M. So it would be 30 plus 20 divided by 2, which is 25. Then we have to use this lambda M, right? And calculate the error. This is my error. So error is what? Positive. So if error is positive, what is the condition? Lambda H has to be updated. Yeah, lambda H has to be updated. So we update lambda H. It was previously 30, so we update it to 25. Remember, lambda L should still be set at 20. Okay, it will not be updated. Again, we check lambda H is now updated to 25. Lambda L is 20. This is 5, so it is still higher than my very small epsilon. Sorry. So yeah, we were here. So we calculate then lambda M. So we have a new lambda M. We put it into the error expression. So you get negative, okay? So you have to update lambda L now. Lambda L was 20. So you are updating it to lambda M value, 22.5. Lambda H still remains at the value equal to last iteration value, okay? 25. Now you have to continue this until you satisfy this constraint, okay? So maybe few more iterations. After a few more iterations, you will get these conditions satisfied. So the solution will be treated as the optimal solution with this star symbol as the superscript, and the lambda is found as $23.53 per megawatt hour. You just calculate PGs with this optimal lambda, okay? You know the expressions of PGs, and these are your solutions, okay? So this is the lambda algorithm we discussed, and this is another way to view this, because you see the lambdas were basically your lambda M value, okay? The plot here in the x-axis is basically showing you the lambda M values, okay? So basically what it is doing, if you check back closely at the lambda M values, it started from what? 25, right? Then it came back to 22.5. And then finally, so the final solution is in between 25 and 22.5, right?
Yes, sir.
But again, if I just for your interest, if I again go back, we started from 25, we jumped down to some lower value of 22.5, But after the required number of iterations, you see this result is in between those two values. So that means lambda is actually going through some oscillatory behavior. So this is what it is shown here. Okay, lambda 1, let's say this is lambda m1. For our example, it is 25. Then it jumped to some lower value, 22.5. Then it jumped to some other value. Then ultimately it will come, only 3 values are shown here. But finally it will come to such a value where your error is almost 0, right? This is the error. So error is almost 0. So lambda is basically fluctuating, oscillating from high value to low value, then jumping back to some other high value. Then probably it will move like this. If I try to draw this, it is moving like this. It is going there, it is coming here, and it will go there, come here, and finally it will, okay, it's basically going like this. So with time, okay, so the drawing is very difficult. So this is how it's going on. So finally it will come down to the optimal point. Okay, so it is actually oscillating from high value to low value, then again coming back to some other high value, then coming back to other low values, and finally it will give you the solutions. So for our example, this is what is actually happening. This is what is actually happening. Okay, so it started from some very high value of error. Okay, and then the error came down to some negative value. Remember, the first error was positive, then we came down to some negative value, and then again positive, then again negative, again positive. You see the oscillation. Finally, probably within 10 iterations, you will come to some